Hello, welcome to this lecture. In this lecture, we'll prove four-vertex theorem. So four-vertex theorem, it states the following. So suppose you take a closed regular planar curve, which is also convex. So then there exist 4 points such that at all those 4 points, the derivative of the curvature, it becomes 0. Okay, so this theorem, it has been proved by an Indian mathematician named Syamadas Mukhopadhyay. Okay, so let us try to prove it. Okay, so before stating four-vertex theorem, so let me tell you, so what do you mean by a convex closed curve? So what is the meaning of this convex simple closed curve? So a curve alpha is said to be a convex simple closed curve. So first of all, this alpha is closed, means alpha A is equal to alpha B, and alpha is simple means alpha restricted to the open interval AB is injective. And what is the meaning of convex? And convexity of this alpha means the region bounded by this alpha is a convex region, and interior of the region bounded by alpha is a convex set in R2. Okay, so suppose this is my alpha. Yeah, so this is my alpha. So this is uh, convex means, so if I take any 2 points inside this region, so the line segment joining x and y, it lies totally inside this region. Okay, so this is the meaning of convex set. Okay, so therefore I have defined a simple closed curve which is convex. Okay, so I have defined this thing. Okay, so now what do you mean by vertex of a regular curve? So let us take a curve which is regular. So a vertex of a regular curve is a point alpha t, where this t, it belongs to this open interval, such that the curvature uh, curvature k at alpha t, if you take the derivative of this k at alpha t, so it becomes 0. Okay, so this k prime at the point alpha t, so this it is a function of t, so let me write like this. So k prime t is equal to 0. Okay, okay, all right. For example, so if you take a circle, so if you take a circle, so this is uh, a convex simple closed curve, and if I take any point on this circle, so the curvature is constant. So therefore, the derivative of the curvature is equal to your 0. Okay, so if I take this point, uh, so k prime t here is equal to 0, since kt is constant for the circles. Okay, so this is example 1. And now if I take this ellipse, okay, so if I take this ellipse, uh, so I can get hold of points in this ellipse where the curvature is maximum and minimum. Okay, so at these points, so you can check that the curvature is uh, 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 it attains the extremum value. Okay, so at this point, so this k prime t will be equal to your 0. Okay, so these are my 4 vertices for this ellipse. Okay, so now let us take any uh, regular simple closed curve which is convex. So we'll prove that. So there exist at least 4 vertices. Okay, so this is due to mathematicians Syama Das Mukhopadhyay. Okay, so let me state the theorem. So a simple closed curve, say simple closed convex curve in R2 has at least 4 vertices. Okay, so this we are going to prove. So how do you prove this thing? So let us take, so let alpha be a simple closed curve. Okay, so a simple closed convex curve. So convex, so here it will be also regular also. Okay, so let alpha be a simple closed convex regular curve in R2. Okay, and so this parameterization I have taken it to be arc length parameterization, and the parameterization is taken to be of arc length. Okay. So now, so if I take the curvature function, so take the curvature function. So it is a function from this interval to R. Okay. So Ks is the signed curvature of alpha at alpha s. Okay. Okay. So first of all, note that this function is continuous. So K is a continuous function. So therefore, it will attends its maximum and minimum value. Okay. So so there exist uh, 2 points S1, S2 belonging to this interval 0L, such that K S1 is say maximum and K S2 is minimum. Okay. So at this extremum points, this K prime, it will be equal to your 0. Okay. So K prime S1 is equal to 0 and K prime S2 equals to 0. Okay. So therefore, so we have at least 2 vertices. Okay. So therefore, alpha has at least 2 vertices, alpha S1 and alpha S2. Okay. So okay. So let us take P to be my alpha S1 and Q to be my alpha S2. Okay. So let us now draw this curve. So suppose this is my P and this is my Q. Okay. So because this curve is given to be convex, so now if I take the line segment joining P and Q, it will lie inside the region bounded by this curve alpha. So this is my curve alpha, and if I take the straight line joining P and Q, it will lie inside this alpha. So this line, it divides this alpha into two segments. Okay, so let us call this to be my beta and this to be my gamma. Okay, so first, so what will show is the following. So suppose this is my line L and you take a unit normal vector perpendicular to this line L. So take a unit normal vector like this. Okay, so what will show is the following first. So first claim is, so if I take this integral, so this integral so alpha s dot product with n. So n is a constant vector, so take the dot product. So this integral, so this will be equal to 0. Okay, so this first will prove this thing. So in order to do this thing, so first observe that so this integral is equal to 0. So this integral is equal to 0, 0. So alpha, so it is a alpha s, it is a vector in R2. So this integral, so it will be equal to your 0, 0. Okay. So how to show this thing? So what is the proof of subclaim? So you do the integration by parts. So this is equal to yeah, so this is equal to your KS, sorry, KL alpha L minus K0 alpha 0 minus this integral 0 to L Ks, then you have alpha dot S. Okay, so we have this thing. So now this alpha L is equal to alpha 0. So therefore, the first term will be equal to your 0. So we have 0 minus this integral. So as alpha L is equal to alpha 0. Okay. So therefore, what we have now, so this integral, so this is equal to minus of this integral. Okay. So now, so next thing, so what you can show is the following. So exercise. So exercise is the following. So this, if I take, so this is my curve alpha. So we have this tangent vector, which is my alpha dot s, and we have this unit normal vector ns. Okay. So exercise is the following. So if I take the derivative of the normal vector, so this will be equal to ks times alpha dot s. Okay. So okay. So once you prove this exercise, so then, so this integral will be equal to minus 0 to L derivative of this normal vector. Yeah, so we have this integral, and this is equal to minus of n L minus n 0. Okay, so again alpha 0 is equal to alpha L. So because of that, so this normal vector at that point will be equal. So this is equal to your 0. Okay, so therefore we have proved the subclaim, and so now to prove the claim, so take dot product with the constant vector n. Okay, so therefore what we have, so this integral is equal to your 0. Okay. Okay. So now again let us go back to that diagram. So we have 2 points P and Q. So this P and Q are the vertices. So this is a vertex and Q is a vertex. Okay. So suppose there does not exist any other vertices. Okay. Okay. So suppose alpha does not have any other vertices. Okay. So this is my beta and this is my gamma. Okay. All right. So now if I take this derivative k prime s on beta, and you take the derivative k prime s on gamma. So note that here this k prime s is equal to 0, and here also this k prime s is equal to 0. Okay. So on beta, so this k prime s, so either it can be always greater than 0 or it can be less than 0. Okay. So k prime s, so on beta it is greater than 0, and k prime s here, it will change the sign. So if on beta k prime s is greater than 0, then on gamma this k prime s will be less than 0. Okay. 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 So, so if alpha does not have any other vertices, so this will implies that. So this implies this k prime s greater than 0 on one segment and k prime s is less than 0 on other segment of alpha. So without loss of genitive, let us assume, so let this k prime s greater than 0 on beta and k prime s less than 0 on gamma. Okay, all right. Okay, and also now we have this line also. Okay, so now if I again go back to this integral, so this integral 0 to L dk ds alpha s dot product with n ds. So this you can divide as follows. It is 0 to L1 yeah. So this point okay, so let me write like this. This 0 to L1 dk ds alpha s dot product with n ds plus L1 to L dk ds alpha s dot product with n ds. So this integral, it corresponds to your beta, and this integral, it corresponds to your gamma. Okay, all right. So now note that, so this is my unit vector over here. So alpha s dot n is greater than 0 on beta and alpha s dot product with n is less than 0 on gamma. Okay, okay, and okay, so therefore, so the first integral, so this is, let us call it to be I1 plus I2. Okay, so then because of this dot product on beta is 0 and derivative of k on beta is 0. So I1 is greater than 0 and also I2 is also greater than 0. Okay, so this implies that this integral is greater than 0. Okay, so this is a contradiction. Okay, so therefore I'll have another vertex. So therefore this implies, so there exists a third vertex on alpha. Okay, so let me again draw this picture. So suppose this is my point P and this is my Q, and I have another vertex which is my R. Okay. So this PQR, it will break this alpha into now 3 segments. Okay, and again here this derivative is equal to 0, here the derivative is equal to 0, and here the derivative is equal to 0. Okay, and let us assume again by the same reason, so this k prime s will be greater than 0 here on this part joining P to R, and in the next part, next subsegment, this k prime s, it will be less than 0. Okay, and again in the next segment, this k prime s, it will be greater than 0. Okay, okay, so now observe that, so this in this whole subsegment from R to Q, in this part, this k prime s is greater than equals to 0, and this part k prime s is less than 0. Okay, all right. Now if I take the line segment R to Q, okay, if I take the line segment, so again by the same reason, so by the same reason, the integral will be positive. Okay, so again, which is the contradiction? So as we have shown that the integral is equal to 0. Okay, so therefore, so this contradiction will tell you that there will exist another vertex. So this implies there exists a fourth vertex on alpha. Okay, so this is the proof of four vertex theorem. So thank you. So I'll stop here.